Let's look at some examples of how we can use the binomial coefficient. So for instance, suppose we want to determine the number of ways we can flip a coin whose flips are independent of one another 4 times and see 2 heads. It might not be immediately obvious how we can use the binomial coefficient to answer this, but another way of thinking about this is how many different ways can we order the string HHTT, where H's correspond to heads and T's correspond to tails. Each ordering of this string corresponds to a sequence of 4 coin flips. One way to think about this is that we have 4 positions, right? Because we have 4 flips. What we want to do is choose 2 of these positions to contain a heads. And by default, the other 2 will contain whatever's not a heads, which is a tail. So we can use 4 choose 2 to determine the number of ways we can flip a coin 4 times and see 2 heads. And if you don't believe me, here they are enumerated, right? We have head, head, tail, tail, head, tail, and so on and so forth. There are 6 of them, and that is 4 choose 2. Another example is, suppose we have a bag of marbles and some of them are blue. How many ways can we draw 7 marbles such that 4 are blue and 3 are not blue? Again, an equivalent way of thinking about this is we have 7 positions or 7 draws. Choose 4 of them to be blue. By default, the other 3 will not be blue. And so we can use 7 choose 3 or 7 choose 4, they happen to be the same thing, to determine the number of ways we can do this. And you can interpret 7 choose 3 as being, I have 7 positions, fill 3 of them. How many ways can I fill 3 of them? With marbles that are not blue. 7 choose 4 is, I have 7 positions. How many ways can I fill 4 of them with marbles that are blue? And so these examples and algebra actually imply that n choose k is the same as n choose n minus k. And you can see here, the numerator is n factorial in both cases, and the denominator, if you just had n choose n minus k, would be the exact same thing. You would just swap the positions of n minus k factorial and k factorial. The reason this works is because n minus k is just k. So the binomial coefficient is symmetric in that regard. So now you may be wondering, well, I thought you told me that the binomial coefficient is for when order doesn't matter. How are we able to just use it to determine the number of orderings of 2 heads and 2 tails when the whole point was that order doesn't matter? And the important thing to realize here is that the order in which we declare the positions is what doesn't matter. The contents of each position does matter. And as an example, let's take a look at the top right. Consider the sequence heads, tails, tails, heads. One thing I could do is say, the first flip is heads, the second is tails, the third is tails, and the fourth is heads. Equivalently, I could say, the second flip is tails, the third is tails, the first is heads, and the fourth is heads. Or I could say, the first is heads, the third is tails, the fourth is heads, and the second is tails. All of these are equivalent ways of stating the sequence heads, tails, tails, heads. And these are all the same thing. They are not different orderings of head, tail, tail, head. These are just different ways of stating what the contents of each position are, but the ordering itself is the same. So all of these, like the ordering of how you present these statements, is what doesn't matter, and that's why we can use the binomial coefficient. Another example that might help clarify things is thinking about it in this other way. Again, we will look at the example of how many ways can we flip a coin 4 times and see 2 heads. Again, this is equivalent to determining the number of rearrangements of head, head, tail, tail. One thing we could do is label the 2 heads and 2 tails with numbers. So we can call them H1, H2, T1, and T2. These are 4 different objects, and so there are 4 factorial ways to order them. But you may notice some of these orderings are really the same thing. So for instance, H1, H2, T1, and T2, that's really the same thing as H2, H1, T2, and T1. And those are both the same thing as H1, H2, T2, and T1. Right? Because the heads are in the same positions both times, and the tails are in the same positions both times. And we have no way of distinguishing between what H1 is and what H2 is. These should all count as one ordering, and as we did before, we need to divide by the number of times we've overcounted for each arrangement. So you might notice the number of ways I can arrange the two heads amongst another is 2 factorial, right? If I had 3 heads, it would be 3 factorial. So what I need to do is divide my number 4 factorial by the number of ways I can rearrange the heads amongst themselves, which is 2 factorial. I also need to account for the fact that the 2 tails are also redundant, and there are 2 factorial ways to arrange them amongst themselves, and so I need to divide my quantity by 2 factorial. And so by dividing by 2 factorial times 2 factorial, I make it so that all of these arrangements, H1, H2, T1, T2, and H2, H1, T2, T1, all get collapsed into the single unique arrangement, HHTT. And so the result we get here is 4 factorial divided by 2 factorial times 2 factorial, which you might recognize as being 4 choose 2. And so this is another way of thinking about the exact same problem, but both ways of thinking about this give you the same result. In this case, that's 4 choose 2. Let's wrap up by extending this idea to multiple categories. Let's suppose I want to count the number of ways I can select 7 marbles from a bag such that 4 are blue, 2 are green, and 1 is red. As an example, I have here 3 of those such sequences. So for example, we could have blue, green, blue, 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 green, red, or blue, 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 red, green, blue, green, so on and so forth. I want to count the number of such sequences that exist. And once again, there are 2 ways I could go about thinking about this. So one way is by saying, well, I have 7 positions in which I could put a marble. Let's choose 4 of them to contain blue marbles. And so now I have 7 positions, filled up 4 of them with 7 choose 4. I have 3 positions remaining. Of those 3 positions, let's choose 2 of them to be containing green marble. Okay, and so I multiply by 3 choose 2. 3 positions put green marbles in 2 of them. In the 1 remaining spot, I need to put a red marble, and so I multiply by 1 choose 1. And so that is one way to determine the number of sequences of this form. It's equivalently the number of ways I can select 7 marbles from a bag, where 4 are blue, 2 are green, and 1 is red. And one thing to note is that I could have instead chosen, the red marble first, and then the green ones, and then the blue ones, or I could have done, the green first, and then the red, and then the blue. The order in which I select these marbles does not matter, and you could work out the algebra yourself if you wanted to, and show that these all come out to be the same result. Another way of thinking about this is, well, I have 7 marbles, I have 7 positions in total, which I can arrange in 7 factorial different ways. So I start with 7 factorial. But I then notice that my 4 blue marbles are actually identical to one another. They're indistinguishable, we sometimes say. And so to account for the fact that they're all really the same thing, I divide by the number of ways I can arrange the 4 blue marbles amongst each other, which is 4 factorial. So I take my 7 factorial and divide it by 4 factorial. I then, again, have the fact that my green marbles are also double counted. And so since I have 2 of them, I need to divide by 2 factorial to account for the fact that they repeated. And then for my red marble, there's only 1 of them, but to show symbolically, I divide by 1 factorial as well to account for the repeats in the red marble. But 1 factorial is equal to 1, so this doesn't really change anything. So this is also equal to the number of ways I can select 7 marbles from a bag, where 4 are blue, 2 are green, and 1 is red. These 2 interpretations are equal, and that should be of no surprise to you. This is not the class where we are going to algebraically work out and prove that these 2 things are equal, but if you really wanted to, you could do that on your own.